Alright, so what we're going to be working on right now is the proof on page 255, which is the equidistant chord converse theorem. In this theorem, we're trying to prove the converse of the theorem on page 254, which had originally said if we have two congruent chords in a circle, then they must be equidistant from the center of the circle. Well, in the converse, we are given that they are equidistant from the center of the circle. We're trying to prove that these two chords must be then congruent. Here's what's given to us in addition to that. Other than the fact that we know they're equidistant, we are also told that OI is perpendicular to DR and OE is perpendicular to CH. And that's what gives us the distance between the chords and the center of the circle. We're going to go ahead and prove that these two chords are congruent. Well, we're going to first start by constructing triangles. As you are used to by now, we know that most of the time when we're trying to prove segments congruent, within a circle especially, we try to resort to creating triangles and proving them congruent somehow, so we can go ahead and prove their corresponding parts are congruent as well. What I have so far is triangle ROD and triangle HOC. Since these two triangles only have two sides that are congruent to one another, then I cannot go ahead and use the direct triangle congruence theorems that would provide these two bigger triangles are congruent to one another. But I do have other options. I can go ahead and take a look at smaller triangles within the bigger triangles and prove them congruent to one another, and then somehow bring each two triangles together to go ahead and prove that these two triangles are congruent to these two triangles combined. Once I get to that point, I can pretty much go ahead and say that these two segments or chords are congruent to one another. Well, let's go ahead and get started. I have constructed radii in the circle. These four radii are all congruent. These four radii provided me with additional information that say, here we go, let me just go ahead and mark them. I have now triangle IOR and IOD congruent to one another. The reason being is that they are both right triangles that have congruent hypotenuse measures and a leg that's congruent to itself by a reflexive property. So by HL congruence theorem, these two triangles are congruent. I'm going to use the same exact theorem to go ahead and say that triangle EOH and EOC are also congruent because of HL congruence theorem in right triangles. Now, I'm going to go ahead and also link these two triangles together and these two triangles together. Once I've linked these two together as being congruent to one another, then I've pretty much created a link between all four triangles, and then I can say by substitution or transitive property, depending on how you write it, all four triangles are going to be congruent. So here's what I'm going to do. IOR is congruent to EOH because they have the same hypotenuse measure, being radii in the circle, and because OI and OE are congruent because they are given to be equidistant from the center of the circle. Therefore, these two triangles are congruent by HL, right triangle congruence theorem. Now I can go ahead and safely say that all four triangles, EOC, EOH, IOD, and IOR are all congruent. Now that I've proven all these triangles congruent, I need to go ahead and figure out a way to say RD is congruent to CH. Well, that shouldn't be too difficult if we keep in mind that IR and ID make up chord DR. EH and EC make up chord CH by segment addition postulate. Now we can go ahead and say ID is congruent to IR because of CPCTC. EH is congruent to EC because of CPCTC. I also know that IR is congruent to ID, is also congruent to EH, is also congruent to EC. All these individual segments are congruent to one another. Therefore, adding up any two of them will give me the sum of congruent segments when I add up the other two to one another. So if I can go ahead and say IR plus ID equals DR, EH plus EC equals CH, but since these two make up the larger segment and they're congruent to these two, then the larger segments must be congruent as well by substitution property. Therefore, I can go ahead and safely say chord DR is congruent to chord CH. And that proves our theorem of equidistant chord converse.